Okay, just to talk a bit more about uncertainties. There are three ways that we can express uncertainties. The first is by talking about the actual uncertainty. The actual uncertainty being the maximum amount by which we think a measurement could be out by. So when we were talking about a meter rule, the uncertainty might be quoted as plus or minus 1 millimeter. So I want you to look up and write the dictionary, or you can look at the web and write down a meaning for what we mean by actual uncertainty. Fractional uncertainty, we simply take the actual uncertainty and divide it by the measured value. So that's going to give us a decimal. It might be might be 1 millimeter. If we took a reading of 10 millimeters, if the uncertainty was 1 and the reading itself was 10, therefore 0.1. That'd be a fairly large uncertainty. And then all we do to get a percentage uncertainty is we take the fractional uncertainty and multiply by 100. And so in the case above, it would be a 10% percentage uncertainty. I myself tend to prefer to work with percentages rather than the fractional values. And the term fractional is a bit misleading because we actually quote it as a decimal. Right, so I want you to write down the definitions of those three terms first of all. All right, let's look at an example then. If we're using vernier calipers and the calipers read to plus or minus 0.01, then the actual uncertainty then is, really we should probably have a plus or minus in there. Wow, it's debatable I suppose, but the actual uncertainty is 0.01 centimeters. If we want to then work that out as a fractional one, we do 0.01 divided by 2.34. And so 4.3 by 10 to the negative 3. If we then take that answer down there and multiply by 100, we get a percentage uncertainty of 0.43%. And that's a pretty small uncertainty in our reading. So I want you to put that example in your notes, please. All right, now, sure, we take readings and so on, but often when we take readings and measure things, we will then want to do something with those readings and combine them together in some way using a formula perhaps, where we multiply or we add or divide, etc. And so there are rules for how we combine those uncertainties together. I'm going to quote you the rules, and then a bit further through the slides, we'll try and show why those rules work without you having to actually copy down those reasons. Okay, so rules for addition and subtraction. The simple rule, and I want you to write these rules out then, is that when you're adding or subtracting, you always add the actual uncertainty. So even if you're subtracting, you still add the uncertainties. Once you've figured out the uncertainty, then you should always round the uncertainty off to one significant figure. And then finally, you round off the quantity itself to the same number of decimal places as the uncertainty. So write out those rules, and then let's have a look at some examples here. All right, so a student attempts to measure the diameter of a steel ball by using a meter rule to measure 4 similar balls in a row. The positions of the scale are shown there. And so we've got one reading there, we've got another reading there. And so if we're going to figure out the diameter, first of all, of the 4 steel balls, we're going to be subtracting the reading here from the reading there. All right, so let's turn to the next slide and see what that might mean. All right, so there's our X value, our Y value. The combined diameter then is going to be 5 minus 1, so 4.0 centimeters. Now, what's the uncertainty going to be? If we were tempted to subtract the two uncertainties, then we'd get 0. Now, that's a nonsense. So what we do, according to the rule, is that we add the uncertainty, so plus or minus 0.4 centimeters. Now, in this particular case, we've already got this to one decimal place. So, well, that's first of all to one sig fig, I should say, over here. And then the same number of decimal places in there. So we do not need to do any more than what we have done here. All right, and so 4.0 plus or minus 0.4 centimeters. So the diameter of one ball would be 1/4 of that, 1.0 plus or minus 0.1 centimeters. And so effectively also by using this process of measuring 4 balls, dividing by 4, we've managed to get our uncertainty down here, all right? Not a particularly low uncertainty, 10%, but that's what the example produces. All right, if we multiply or divide, instead of working with actual uncertainties, the key thing is to work with fractional. I would prefer myself to work with percentage uncertainty. So instead of adding actual uncertainties, we add percentage uncertainties, and then rules 3, 4, 5 are really just, or 4 and 5 are really just the same as for addition and subtraction. So again, write those rules out, please. And let's have a look at an example here. All right, so mass of a stone found to be 78.4 plus or minus 0.2 grams. And then we've also got the volume. So we're going to use the formula density equals mass divided by volume. All right, so I'm not going to go through the calculations. You can do that, but it's going to be 22. I'll get it right around, sorry. Let's get it right. 78.4 divided by 22. Let's try a different color, might be more clear. And then from there, you can work out a value. You may get a whole string of decimals. Don't worry at this stage. Right, uncertainties. The way I'd be doing it, percentage uncert in M equals 0.2 divided by 78.4 times 100 equals percentage uncert in V equals 2 divided by 22 times 100 equals. I think we can see that the uncertainty in the volume is larger than that in the mass. So therefore now the percentage uncertainty in the density, we add that percentage uncertainty there to that percentage uncertainty there, and you get the total percentage uncertainty. Having figured out that total percentage uncertainty, we then figure out what is that percent of the actual density. And then we go into the rounding rules. We round the uncertainty off to one significant figure. We round then the density value itself off to the same number of decimal places. I will give you the answer to this problem in class so that you'll be able to check whether you've done this correctly. But I want you to work through that example yourselves, please. All right, what happens if you're using powers of 10? What happens if it's a formula that involves powers of 10? Well, when you square something, you are really multiplying a number by itself. If you cube, you're multiplying a number by itself twice. So the rule for powers is that you multiply the percentage uncertainty by the power. So if you're squaring, it's 2 times the percentage uncertainty. Cubing, 3 times. Square root, the power is 1/2, so it's half the percentage uncertainty. Okay, so up through the previous slides is what you need in your notes. These slides here are not for your notes. Okay, this is simply just to give you some idea of what's going on. Okay, so this is just a worked example to show why those previous rules work. So if we've got a length with an uncertainty of 0.1 and another length, if we add those two lengths together, well, this 2.4 could lie between a maximum value of 2.5 and a minimum value of 2.3. The 1.7 could lie between a maximum value of 1.8 and a minimum value of 1.6. So when we add these numbers together, the most extreme situation would be that the largest value of one and the largest value of the other add together to give us 4.3. And the opposite extreme would be the two smallest values adding 3.9. Adding together the actual values themselves, 4.1, but what do we notice? The uncertainty now between 4.1 and 4.3 and 4.1 and 3.9, the uncertainty has become 0.2. So when we add, effectively, addition of the uncertainties takes account of what would happen in practice in terms of those errors or uncertainties. If we subtract, same sort of logic again, but this time we would take the largest possible value from the 2.4 minus the smallest would give us the biggest difference, 0.9. And then if we take the smallest possible value that we could get from that, which is 2.3, and subtract the largest possible value we can get from that, we get the smallest difference, 0.5. Taking the actual values themselves, 2.4 minus 1.7 gives us 0.7. But looking at these two extreme situations, what's the uncertainty? Plus or minus 0.2. If we multiply, so we've got our two values, L1, L2. I've already worked out that 0.1 is 2.1%. This 0.1 is 6.3% of that value there. So the maximum possible product that we could get, 4.8 plus 0.1, 4.9, 1.6 plus 0.1, 1.7. The maximum possible value, 8.33. Similar logic using the minimum values, 7.05. So if you have a look at that, the actual average value is 7.68. This 8.33 is 0.65 above the average. This 7.55 is 0.63 below the average. If you combine these two uncertainties, 2.1 here plus 6.3, we would get 8.4%. If we work at 8.4% of our answer, what do we get? 0.65, which is almost the same as our 0.6 or 0.645, almost the same as our 0.63, our 0.65. So if we round that off, we can see we're pretty much in the right ballpark, plus or minus 0.6. So don't get hung up if you're having trouble following these examples. Don't be too worried about it. It's simply to give you, the explanation as to what's behind it. And similarly for division. For division, if we want to get the biggest possible value, we take the largest divided by the smallest. We take the smallest divided by the largest. Those are the two figures that we're out by compared to the sort of the average value. Add you two percentages together again, 8.4%. 8.4% of the answer is 0.252, 0.252 rounded to one significant figure, 0.3. And so, the rules that you've written down earlier work. Okay.